So we know that initially when the plates are charged, they will have a potential difference and there will be an electric field starting from the positive end and going to the negative end. It will split into three components, that is Q1 will be entering here, Q2 will be entering here, and finally Q3 will be entering into the third capacitance. As a result of positive charges being accumulated on top of the plate, there will be a negative charge induced on the other plate. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were studying about capacitors and its effects. And today we are going to study about what happens if I put a dielectric in between capacitance, what will happen to the capacitance, how can we calculate the capacitance, and what is going inside the capacitors. So let us dive into it. So we were dealing with capacitors, especially parallel plate capacitors. So we were dealing with parallel plate capacitors, that is. Now, what happens if I charge this particular capacitor? So I can say that if I connect this particular capacitor to a battery of V volts, then I can say that this parallel plate capacitor will be charged. That is, it will develop a positive charge on the top plate and a negative charge on the bottom plate. So there is obviously a potential difference between the two plates. One will be positively charged, let's say this is positive Q, and the other will be negatively charged, let's say that will be negative Q. Now what I'm going to do is that instead of air being the medium in between these two parallel plate capacitors, I'm going to introduce a dielectric medium. So we already saw that dielectrics are basically insulators. They prevent the flow of current. So what happens if I place a dielectric in between these two parallel plate capacitors? So let's see. So initially I'm going to assume that the charge density on these particular plates are denoted by sigma. So obviously sigma here and minus sigma here. So don't forget, sigma is the surface charge density, which can be written as charge per unit area. So I am taking the assumption that the surface charge density of this particular parallel plate capacitor is sigma on the top plate and negative sigma on the bottom plate respectively. And what happens if I place a dielectric medium in between these parallel plate capacitors? So we know that initially when the plates are charged, they will have a potential difference and there will be an electric field starting from the positive end and going to the negative end. So this will be the direction of the electric field, and let's say for sakes that E0 is the current electric field between the plates, and the spacing, that is the distance between the two plates, is indicated by D. So these two plates are kept at a distance of D. They are placed in a manner that they are D distance apart from each other, and they will have an electric field between them, and that is denoted by E0. The surface charge density is given by sigma is equal to Q by A. So what happens to a dielectric medium when it is placed in an external electric field? We saw that polarization occurs to the dielectric medium. Whether it is polar or non-polar, the dielectric medium will get polarized. So we can say that the particular charge centers in that particular dielectric material will get polarized, and it will be arranged in such a manner that the negative charges will be arranged on the top and the positive charges will be arranged at the bottom. So this will be the state of polarization of the dielectric material. When the dielectric material is polarized, it develops an internal electric field due to polarization, which was discussed in the previous class. So we know that there is a polarization and internal polarization, and the direction of internal polarization will be in such a manner that it will oppose the external electric field. So the direction of internal polarization will be in a manner that it opposes the external electric field. So once again, to simply clarify, when we place a dielectric material in between parallel plate capacitors, where there is an electric field E naught, the dielectric material will develop an internal electric field to oppose the external electric field, and the top part of that dielectric medium, which is close to the parallel plate, which is close to the top plate, will be partially negatively charged. That is, because of the presence of the dielectric material, this plate will be, or the top portion will be, negative sigma p, because the dielectric medium introduces the negative charges just below the top plate, so it is negatively charged, and that is indicated by negative sigma p. Just like that, on the bottom plate also a positive charge develops to oppose the electric field, and that is indicated by positive sigma p. So this will be the case. So initially the plates were positively and negatively charged, and when we placed a dielectric medium in between that electric field, because of the result of polarization, another electric field was generated which is in the opposite direction, which actually reduced the surface charge density. So the net surface charge density, let's say of plate A, which is the top plate, can be written as sigma total is equal to sigma minus sigma p. That is, if the initial charge density of the top plate was indicated by sigma, then sigma p, that is, the charge density due to polarization, that is indicated by negative sigma p. So the difference between them will give you the total net charge density on the top plate. In the bottom plate also, we can write it as sigma is equal to negative sigma plus sigma p. So I can actually write it as negative of sigma minus sigma p. So we can take the general assumption that sigma is directly proportional to sigma minus sigma p. As the value of sigma increases, it will be proportional to sigma minus sigma p. So that is the assumption we are taking from these two equations. So considering the initial considerations, that is surface charge density, what is the net surface charge density, we are going to calculate what is the net electric field in between those two parallel plates. So we know that the equation for electric field is given by E is equal to sigma by epsilon naught, which was also discussed in the previous topics. So we know that sigma can be written as Q by A. But for now, we are not going to write it as Q by A. We are going to write it as the total charge density of that particular parallel plate capacitor. So we can write it as sigma minus sigma p divided by epsilon naught. So we are going to keep this aside here. So this is how we can express the charge density of that particular parallel plate capacitor in between which a dielectric material is placed in terms of electric field. Now the equation is not over because it is slightly a bit complicated. So we are going to reduce it down even further. For that, we are going to assume the relation that sigma is directly proportional to sigma minus sigma p. So we are going to consider the fact that sigma is directly proportional to sigma minus sigma p. From this relation, we know that this is a proportionality sign, and in order to avoid that proportionality sign, we have to introduce a constant of proportionality. And the constant of proportionality we are going to introduce here is known as K, which is a dielectric constant. So K is a dielectric constant. So now we can write sigma is equal to K into sigma minus sigma p, or we can write it as 1 by K into sigma is equal to sigma minus sigma p. Now we have an equation for sigma and dielectric constant. So So remember, the dielectric constant depends on whatever material you are using as the dielectric. If you are using air, it has a particular value. If you are using water, it has a particular value. If you are using paper, it has a particular value. So depending on the substance you are using, depending on the material you are using in between those parallel plates, the value of K changes. So for most cases, it will be greater than 1. Remember, the value of dielectric constant will be greater than 1 for most cases, and it will only be equal to 1 when you are using a specific medium, let's say like vacuum or air, then it will be equal to 1, but otherwise it will be always greater than 1. Now what I'm going to do is that I'm going to substitute this particular result into the equation we just found out. So I can write E is equal to, E is equal to sigma by K, because sigma minus sigma P is equal to sigma by K. So I'm going to write sigma by K into epsilon naught is equal to E. Now this is not done. To find the net electric field, we use one more thing in this relation that states that this particular electric field is equal to sigma by epsilon naught. We already know that sigma by epsilon naught is nothing but E. And here, that particular sigma by epsilon naught is the electric field between the two parallel plate capacitors. That is, not including the dielectric which is placed in between the parallel plates. That is, sigma by epsilon naught here is indicated as E naught. So I can write E naught divided by K. This will be the final equation for the electric field of the total electric field in between a parallel plate capacitor in which a dielectric medium is kept. So you can actually say that depending on the dielectric medium being kept, the total electric field of that particular capacitor varies. If it is vacuum, then the K value will be equal to 1 and E will be equal to E naught. If it is water or any other material which have a K value greater than 1, let's say 10, then the electric field will decrease by a magnitude of 10 because it is being added to the denominator. So depending on the dielectric which you are using, the electric field magnitude will also vary. Now finally, we are going to write it in terms of potential also. We know that from the previous topics, V is equal to E into D, because we know the relation E is equal to negative dV by dr. From this we can assume the general relation, which is V by D is equal to E. So ED is equal to V, that is being written here as E into D. So we can write an equation for potential also, which is equal to E naught into D divided by epsilon naught, or simply V naught divided by epsilon naught to find the potential. Remember, E naught is the electric field between the parallel plates and D is the distance between the two plates. Generally, the distance between two parallel plates will be very small in the order of millimeters or even micrometers or nanometers. So capacitors are very, very, very shortly spaced. So this particular equation will give you the new potential for that particular parallel plate capacitors. So remember, first we consider two parallel plate capacitors, and then first we considered a parallel plate capacitor in which a dielectric medium was kept, and due to the electric field between the two parallel plate capacitors, because of the electric field between the parallel plate capacitor, the dielectric medium became polarized and there developed an internal electric field. And finally, because of the internal electric field, the total charge density of the system became a different quantity which was expressed in terms of electric field, that is E is equal to sigma minus sigma P divided by epsilon naught. But finally, we arrived at the conclusion that sigma, that is the total charge density, was directly proportional to sigma minus sigma P. And then we introduced a proportionality constant and we got this particular result. And then we substituted that result and we got this relation for electric field of a particular parallel plate capacitor in which a dielectric medium was placed, and finally we arrived at another equation which denoted the net potential of that particular capacitor in which the dielectric was kept. So what is the use of keeping a dielectric in between a parallel plate capacitor? The obvious reason is that when the dielectric material was placed in between the parallel plate capacitor, the net potential of that system went down. Since the net potential is going down, which means that the total capacitance will go up because this is K. Okay, so since the net potential is going down because K value for any other medium other than vacuum or air is greater than 1, we can say that the V value will decrease. That is, the net value of potential will be going down in a system where a dielectric medium is placed between the capacitors, which means that the net potential goes down, which also we saw in the other topics that if the potential goes down, the net capacitance goes up. So the use of placing a dielectric in between two parallel plate capacitors is that the net capacitance goes on increasing. So that is the effect of a dielectric on capacitors. So if you place a dielectric in between a capacitors, then the total capacitance will go up because the net potential goes down, which means the capacitance goes up because C is inversely proportional to V. So that is why the net potential goes down and the capacitance goes up. Remember, here it is not epsilon naught, it is K, and here also it is K because we are substituting E into D, which is an equation for potential. So here it is K and not E naught. Moving on, we are going to find out what happens when we are arranging capacitors in series and in parallel. If you have observed circuit boards, we can see that there is not exactly just one capacitor, but there is a number of capacitors being arranged in such a manner that they can be arranged in series or in parallel in a circuit. So we are going to look at what happens when you arrange capacitors in series and how can we calculate the total capacitance of that particular system. So let's assume that we have a circuit where capacitors are arranged like this. So in this particular circuit, let's say I have connected a cell having V potential. Then this will be positive, this will be negative, and this V potential is being allotted to three capacitors, that is capacitor C1, capacitor C2 and capacitor C3. So from this V voltage cell, Q amount of charge is being carried out and into the capacitor. So Q amount of charge is being stored into this capacitor and this capacitor. One thing to remember is that it is not Q1, Q2, Q3 charges being stored. It is just Q amount of charge being stored in this each capacitor. So we can see that when this capacitor gets charged, that is, here it will be positive Q, here it will be negative Q. Why? Because when the charge get accumulated, here it will be positively charged, and then automatically on the other plate it will be negatively charged. So one will be positive and one will be negative. This will induce a charge on the next capacitor so that the capacitor next to that will also get positively and negatively charged. One thing to remember is that it is not Q1, Q2, Q3, it is the same amount of Q being stored in this individual capacitors. So here, here and here all is the same amount of Q. How is that possible? I'll just prove it to you in just 1 second, but assume that this is the manner in which the capacitor is being arranged, one after the other. That is, they are arranged in series manner. We know the initial relation, that is Q is directly proportional to V. From this, we know that the equation for capacitance is Q is equal to CV. But we know that the amount of Q being stored in each of these capacitors is the same Q. So we know that Q is not changing, but the potential across all of these capacitance are different. So initially for capacitor C1, the potential is V1. For capacitor C2, the potential is V2, and finally for capacitor C3, the potential is V3, which means that Q is not changing, V is the only quantity which is changing. So I can write it as Q by C is equal to V, or simply I can write it as Q by C1 is equal to V1 and Q by C2 is equal to V2, and finally Q by C3 is equal to V3. So in order to find out the net potential across these three, we have to only add them together, which means that net potential V net can be found out through V1 plus V2 plus V3, which is equal to Q by C1 plus Q by C2 plus Q by C3. So adding this together, we will get the net potential, that is V. So we can see that Q is common everywhere. So I'm going to write this particular equation in a different form, and that different form is that we know the equation V is equal to Q by C, which means that V net is equal to Q net divided by C net. So I can write this as Q by C is equal to, let's say this is the net capacitance, is equal to, this is the net charge also. Since charge is not different anywhere across the capacitors, I can just simply write it as capital Q. And Q is common everywhere, so I'm taking it outside, Q into 1 by C1 plus 1 by C2 plus 1 by C3. That is, I can cancel out the Q's and simply write 1 by C net is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the equation in order to find the net capacitance. So we'll get only 1 by C. In order to find out the net capacitance, we have to turn it ulta. I'll show you an example for that. But firstly, listen to what we just did. So we assumed a circuit and we assumed three capacitors being arranged in series. So it had a potential of V1, V2 and V3. And we know that the charge across these three capacitors are same, coming from the voltage V. And we knew the relation, that is Q is equal to CV. From that we formulated an equation for potential, which is Q by C is equal to V. So from that we know that V is changing, that is V1, V2 and V3 across C1, C2 and C3. So in order to find out the net potential, we added the potentials of that system, that is V1, V2, V3, which can be written as Q by C1 plus Q by C2 plus Q by C3. Q is same because Q is not changing everywhere, it is just Q charge being stored. So we can write this Q by C1, that is Q by C is equal to V. So that is why we are writing V net as Q by C into Q into 1 by C1 plus 1 by C2 plus 1 by C3, because we can take out the common factor Q outside. Cancelling out the Q's, we get 1 by C net, that is the net potential of that particular circuit, can be found out through calculating the reciprocals of each of the individual capacitors. For example, let's say that this particular circuit had a capacitance C1 is equal to 1 mu F, C2 is equal to 2 mu F and C3 is equal to 3 mu F. Then what will be the net capacitance of that particular circuit? So we know from the formula that the net capacitance can be written as 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So it can be written as 1 by 1 plus 1 by 2 plus 1 by 3. So I can write it as 1 by 1 plus 3 plus 2, 5 by 6, which can be written as 11 by 6. And finally, I got 1 by C. In order to find out the net capacitance, I am going to write C is equal to, flip this over, that is 6 by 11 microfarad. Or finally, we can write it as 6 by 11 into 10 raised to minus 6 farads. So this will be the net capacitance of that particular circuit. What we are doing right here is now reducing the circuit into a simpler form. That is, we are assuming that the capacitance of this will result in a circuit that will look like this. So this will be C net and this will be voltage. So the idea is that when we add up these individual capacitance together, it will condense down into a simpler circuit like this so that we can calculate C net. That is why we are calculating C net. So the circuit condenses down and we'll get the total capacitance so that it acts like that. That is like an individual capacitor. That is how we reduce a circuit into that particular form. Now the question arises, is it only the way to arrange capacitors in series? No, we can also arrange them parallelly to each other. So series is when one repeats after the other and goes on. Parallel is when one is stacked on top of the other like that. So let's assume a circuit where positive, negative, a cell is connected and V voltage plus minus, and from, let's say this is junction A and this is junction B, then I have three capacitors, that is C1, C2 and C3 arranged parallelly to each other. Same considerations, that is V volt is connected to the capacitors so that Q amount of charge enters into each capacitor. That is, up to the junction A, it will be Q amount of charge reaching, but when it reaches the junction, it will split into three components, that is Q1 will be entering here, Q2 will be entering here, and finally Q3 will be entering into the third capacitance, which means that the potential across all three will be same. Here the only factor that differs is the charge. So the potential across that particular capacitors, that is C1, C2 and C3, remains constant, that is V. So V amount of potential is reaching each capacitor, but for the charge reaching each capacitor is different. One is getting Q1, one is getting Q2 and one is getting Q3. So we are going to consider the same equation, that is Q is equal to CV. From this we are going to find out how we can calculate the net capacitance of that particular system. So we know that Q1 gets C1V, we know that Q2 gets C2V, and finally Q3 gets C3V. And in order to find out the net charge of that system, we are going to add it together because charges are additive. So we can write Q1 plus Q2 plus Q3 is equal to C1V plus C2V plus C3V. So what is common in here? That is V. So we can write it as V into C1 plus C2 plus C3, C1 plus C2 plus C3, and we know the equation to be Q is equal to CV. So we can write CV is equal to V into C1 plus C2 plus C3. So we can cancel out the V's here and then we'll get the equation net C is equal to C1 plus C2 plus C3. Don't get confused. This net charge can be written as C1V plus C2V plus C3V, and V is common, so we take it outside and we can write this Q1, Q2, Q3 in the form of CV. That is, net charge can be written in the form of CV. So we are writing CV is equal to V into C1 plus C2 plus C3. and we cancel the V's which are same on both sides, and finally this particular C is the net capacitance which we will get as C1 plus C2 plus C3. That is, the net capacitance of that particular circuit will be equal to the algebraic sum of the individual capacitors. So for example, we can say that if C1 is equal to 1, C2 is equal to 2, C3 is equal to 3, let's say microfarad, then we can write net capacitance to be C1 plus C2 plus C3, that is equal to 1 plus 2 plus 3, that is equal to 1 plus 2 is 3, 3 plus 3 is 6 microfarad, or C is equal to 6 into 10 raised to minus 6 farad. That is how you add up capacitors connected in parallel and capacitors connected in series, and this is the way we derive the results. And just so you know, the system, that is this particular circuit, will condense down into the form So we are trying to condense down the system into this simplified form. Again, same as that for series, we are doing this in order to simplify the circuit. So if you have any capacitors arranged in series, it will be added as reciprocals of their capacitance to find the net capacitance. And finally, if you have parallel plate arrangement, then you have to add them individually like you add any other scalars. So that is something you have to remember. Moving on. Finally, we are going to discuss what is the total energy of a capacitor. That is, if a capacitor is connected to a battery, what will be the total amount of energy stored in that particular capacitor? So we are going to consider a capacitor and a battery connected to that. So let's say we have two parallel plates . So we have a parallel plate capacitor here which is connected to a battery or cell which has V volts. So it has V volts, which means that it is pushing away charges from the battery onto the top of the plate. That is, here dq amount of charge is being deposited on top of the plate by slowly depositing each charge on the plate. So let's assume for a while it is accumulating charges. So let's say in time t1, it is dropping dq amount of charges onto the plate like sprinkling salt onto a table. So we are going to sprinkle dq amount of charge slowly onto the plate. As a result of positive charges being accumulated on top of the plate, there will be a negative charge induced on the other plate. So we can say that here it is negative q and here it is positive q. So charges are being accumulated on the surface and a battery is pushing dq amount of charge is being dropped onto the plate, and the battery is doing work in order to do that. So why are we talking about work? So from the beginning of the chapter, we know that in order to calculate energy, what we done was calculate the work done in assembling a system. That is, if we can successfully calculate the work done in order to assemble that system, it will be equal to the energy of that particular system. In this case also, we are going to consider the work done and we are going to calculate the work done so that we can calculate the energy of that particular system. In this case, the energy stored in that particular capacitor. So we know that dq amount of charge is being dropped into a parallel plate capacitor which has, let's say, C capacitance. So we know that much, and we know V is the potential difference of the battery, and let's say V dash is the potential difference across these two parallel plate capacitors. So we know from the equation for capacitance, that is C is equal to Q by V. So we know that C is equal to Q by V. And finally, we know the equation for work done. The equation for work done is F dot dr, but we cannot use that here. We have to play with the quantities or parameters we have at hand. And here it is not about force or displacement, it is more about capacitance, potential and charges. So we know one more definition for potential, that is V is equal to W by Q. So charge, potential and work done. So in order to find out work done, it will be equal to potential difference times charge. So we can write it in another manner. Let's say this is plate B and this is plate A. Then we can write the work done in assembling that charges can be written as WAB can be written as VB minus VA. The potential difference between B and A will give you the work done per unit charge, or this is the definition of potential as discussed in the first topic. But this particular VB minus VA is nothing but del V or simply V, and we know an equation for V. V is nothing but, from this equation I can write Q by C is equal to V. I got it from the relation, that is CV is equal to Q. From this relation I can write Q by C is equal to V. So instead of this del V, I am going to write WAB by Q is equal to Q by C. So I can write the total work done or the total potential can be written in this manner. This is one form of writing it and this is the same form of writing it in another term. So work done per charge will be equal to charge per capacitance. So again, this is a generalized form. What we want is specifics. What we are actually doing here is a small amount of work. That is, we are trying to push a small charge which is dq onto these plates. So what will be the energy between these two plates? What will be the work done in order to push a charge between these two plates? So I am going to do a small amount of work in order to drop a small charge dq onto that plate. So the work done dw, let's say the small work done is dw and integral of that will be w. So in order to find out the net work done, I only have to integrate that small work done. That small work done or the work done can be written as Q by C dq. Integral from where to where? From the plate was empty, that is the charge was 0, to the charge was maximum, that is Q. So we can write 0 to Q. So when this is capital Q, the plate is completely charged. So in order to calculate the work done from 0 to capital Q, that is from a point of minimum to maximum, we are going to do this work. So the only quantity which is changing here is nothing but Q. So only the Q is being deposited. The capacitance is not changing for that particular parallel plate capacitor. So we can write integral 0 to Q, Q by C dq as 1 by C into integral 0 to Q, Q dq. And we know already that the integral of x dx is nothing but x raised to n plus 1 by n plus 1. So from this relation, I can write down that this implies 1 by C Q square divided by 2 from the limits 0 to capital Q. Upon applying the limits, I can write it as 1 by C Q square by 2 minus 0 by 2. So the final result becomes 1 by C into Q square by 2, which can be written as Q square by 2C. So this will be equal to the work done. This work done will be equal to the energy of that particular system, in this case the potential energy of that particular system. So we can write this W is equal to U, which is equal to Q square divided by 2C. So we got an equation for work done which was given as W is equal to Q square divided by 2C. Now this is equal to the energy stored in the particular capacitor, which is nothing but the potential energy of that particular capacitor. That is, the energy stored inside the capacitor is equal to Q square by 2C. But we can also write down this equation in several other forms. For example, we know the relation Q is equal to CV. So we can write down, instead of Q, we are going to write down CV, so that we get the equation Q square by 2C becomes C square V square by 2C. The C's get cancelled each other and we get CV square divided by 2. This is one more way of representing that particular equation. We can write it in another term, that is Q by V is equal to C. So we can substitute, instead of C we can substitute Q by V. So Q square by 2C becomes Q square divided by 2 into Q divided by V. Q and Q get cancelled and we can write it as Q by 2. So QV by 2. The V goes to the numerator and we can write it as QV by 2. So this is one more way of representing that particular equation. We can also write it in terms of A epsilon naught divided by D if you introduce the term E into D for potential, and there are many ways of writing it, but this is a most condensed form you can write it in. And finally, here we have a representation of the energy stored in between the plates of a capacitor. Finally, there is one more question remaining. We saw that if this was the two plates, if this was the two plates and V was the potential between them and W is the work being done, then we can actually say that W is equal to QV from the relation, that is W by Q is equal to V. So this should be the total work done by the battery in order to push charges onto the parallel plate capacitor so that it is fully charged. So this work should be the total energy of that particular system. That is, U should be is equal to QV. But we just proved that the energy stored inside that particular capacitor is nothing but QV by 2. Almost half of the energy is missing. Where did that energy go? So half of that particular energy was distributed as heat. That is, when the battery is trying to push charges from this battery onto the plates, what happens is that the charges are moving through wires, copper wires, iron wires, silver wires, whatever it is moving through wires. So half of that energy is being spent as heat. So if, let's say, 5 joules of work was done, or 5 joules of energy was spent in order to push that charge onto that plate, only 2.5 joules was stored inside that plate. In between those plates, only 2.5 joules reach, because half of that energy is being spent as heat or is dissipated as heat. So this follows the first law of thermodynamics, which states that energy can neither be created nor be destroyed. It is only transferred from one form to another. So this is the equation, or this is the manner we can find about the energy stored inside a capacitor. And that is all about capacitors, potential and potential energy in this chapter. I hope you have understood all about capacitors, potential and potential differences and potential energy of a system. And I'll see you all very soon with another chapter. Until then, thank you.